So welcome to my task 8.1. This is my video demonstration. So hi, this is my demonstration for task 8.1p. In this video, I'll walk through several graph algorithms including BFS, DFS, and Jarex algorithm. I'll also explain how they work, prove their correctness, and highlight their time complexity. So part A is to basically count the shortest paths in BFS. So part A basically focuses on counting the number of shortest paths from a source node. In an unweighted graph, since all roads have equal weight, we use the first search, which guarantees shortest paths in O(n) plus m time. We'll maintain two arrays, this v to store the shortest distance to each node, and count v to store the number of shortest paths. So if we visit a node from the first time, we set its distance and inherit the path count from the previous node. If we find another shortest path later, we increment the count. So this approach ensures we capture all possible shortest paths to every node from the source. So in the graph, in the bottom right, we can see that A to B is 25 weighted. A to M is 1. If you want to go to AMD, it will be 1 plus 10, which will equal to 11. So basically, an unweighted graph, we use BFS for O(n) plus n time. Track this v, the shortest distance from the source. Track count v, number of shortest paths to v. If new shortest paths are found, increment count v, and ensure all shortest paths are counted correctly. So in part B, we check if a undirected graph is connected. This means we want to know whether every node is reachable from any starting point. So we do this by using a depth first search, searching from any node we recursively visit, all its neighbors, and mark them as visited. Once the travel cell ends, we visit every node in the graph, then the graph is connected, otherwise it's disconnected. This algorithm runs in linear time, so O(n) plus m. When the graph is represented as an adjacent list, making it very efficient for larger graphs. So in this image below here, we can see that on the left it is all connected, as if we start from node 2, let's say, we're able to visit any node from going past each other. So this is a connected graph with a single component. Whereas in the graph on the right, we can see that there is two components. Which is component 1, which is just node 5, that is all alone in an island, whereas component 2 is connected with each other except 5. So this is a disconnected graph with the two different components. So the main idea is that we start DFS from any node. We mark all reachable nodes. If all nodes visited, the graph is connected, and it runs O(n) plus m runtime using adjacency lists. So in part C, we analyze the runtime of DFS when using an adjacency matrix instead of a list. In adjacency matrix, each row represents a node's connection. So to find a node's neighbors, we have to scan the entire row. That takes O(n) time per node. Since we perform this operation for all n nodes, the overall runtime becomes O(n) squared, regardless of the number of edges that exists. So this is significantly less efficient than using an adjacency list, which gives us a runtime of O of n plus m, potentially to the actual number of connections. So in the graph on the bottom right, we can see that an adjacency matrix is shown here. So for node 0, we can see that node 0 does not have a loop, so it is 0. We can see that node 0 is connected to 1, so we mark that as 1, and only connects once, and does not have any other paths that connect to 1. We can see that it does not connect to 2, it does not connect to 3, However, it does connect to 4, but only one path to connect to 4 exists. So the main idea is that the adjacency matrix scans the full row per nodes, which takes O(n) time. The total time, which is would be O big O of n squared for n nodes, and it's less efficient than an adjacency list, as an adjacency list is O of n plus m. So in part D, we walk through Dirichlet's algorithm on a weighted directed graph. We begin at node 1, set its distance to 0, and utilize all other distance to infinity. We use a mim heap property Q to always process the node with the smallest known distance. So in each step, we extract the closest node, update the distance to its neighbors if a shorter path is found, and insert those neighbors into the queue. So as we go, we need to keep track of the shortest distance to every node, as well as the path taken to get there. And at the end, we have to find the final shortest path tree rooted at node 1, and complete the table of distance to all nodes in the graph. So as you can see in the bottom left, our first rule is to basically make sure 3 is no negative edges. So we make sure that there's no negative edges, so the distance is secure the vertex as 0, and set all other distances to infinity, as we said. And then rule 2 is to relax all vertex adjacent to the current vertex. As we can see that this graph, basically all those. And then rule 3, we choose the closest vertex as the next current vertex. And then rule 4, we repeat rule 2 and rule 3 until the queue all reach the distance. So the main idea is that we utilize the distance, so 1 equals 0, others equal to infinity, and use a mim heap. And track visitor nodes and distance, build a shortest path tree from the source, and final distance show the shortest paths to all nodes as well. So in part E, we explore what happens if we increase the weight of every node in the graph by 1. Let's say we have 2 paths. Path P has 3 edges and path Q has only 2. Originally, path P might have been the shortest due to the lower total weight, but when we add 1 to every edge, path P's cost increases by 3, and path Q's by only 2. That smallest increase might make path Q the shortest path now. So increasing all edge weights uniformly does not present the original shortest path. It can change the outcome depending on the number of edges in each path. So the main idea of this is to basically longer the path increase more, so more edges times +1. Shorter paths may now become optional. The original shortest path might no longer be the shortest anymore. And an example of this could be path P, 3 edges, versus path Q, 2 edges. So to summarize my task, we basically went through the BFC to count the number of shortest paths in an unweighted graph, which gives us an efficient O of n plus m solution. We applied the DFS to check whether an undirected graph is connected. We ultimately also analyzed the performance of the DFS using both adjacency lists and matrix, showing that adjacency lists are more efficient as matrix lists total time complexity will be the big O of O(n) squared. We also walked step by step through Dirichlet's algorithm using a real example to understand how it builds the shortest path tree. And finally, we showed that increasing all edge weights uniformly can change which path is shortest due to the number of edges involved. So thank you for listening, and I hope you have a nice day.